Welcome to the Game Engine tutorial series, a Vulkan game engine built from scratch in C++. In this episode, episode 1, we're going to get a window on the screen with Vulkan rendering a clear color. This might sound simple, but with Vulkan, there's a lot of setup required before you can draw even a single pixel. So rather than live code this, I've prepared all the code for you. Let's walk through what's happening. To follow along, clone the repository and check out the episode 1 tag. You will need a C++20 compiler, CMake, and the Vulkan SDK installed. Please check the README for platform-specific instructions. If you install CLine, most of this is handled for you. Just make sure you install the Vulkan SDK for your platform. Link is in the description. Here's how the project is organized. The engine folder contains the reusable engine library. This is for things like window management, rendering, and logging. Sandbox is our test application that uses the engine. Third party is where the CMake fetches our dependencies. These are things like glfw for windowing, glm for math, and speedlog for logging. The goal is to keep the sandbox main.cpp clean and simple while the engine handles all the complexity. So let's start with the sandbox main.cpp. This is really the entire application. We initialize logging, create a window with a config struct, and then create a renderer and pass it to the window. The main loop is pretty straightforward. We just pull for input, update the clear color, handle resizing events if needed, and then begin and end a frame. That's about it. Total is about 50 lines of code. This clean API is the goal, but underneath there's a lot happening. Let's take a look at the engine code. So let's talk about window abstraction. In the window.cpp in the engine folder, lines 25 to 47, the window class wraps glfw. The key detail here is this line, line 27, glfw window hint. Unlike OpenGL, Vulkan doesn't need glfw to create a graphics context. We tell glfw no API, meaning we handle rendering ourselves. We also set up a resize callback using glfw's user pointer pattern. We store this in the window so our callback can retrieve the window object later. The rest is straightforward glfw code: create a window, handle cleanup in the destructor. So let's talk about the Vulkan renderer. Renderer.cpp lines 38 through 56, which is the constructor. This is where Vulkan lives. Look at the initialization sequence. This is the Vulkan initialization ritual. Order matters. Each step depends on the previous one. It looks intimidating, but once it's set up, you rarely touch it again. Let me explain each step. Create instance. This is your application's connection to the Vulkan driver. We specify our app name, engine name, and which Vulkan version we're targeting. Skipping over the debug messenger just for a moment, the create surface, this bridges glfw's window to Vulkan. glfw provides helper functions for this. Physical device. We enumerate the GPUs in the system and pick one that supports what we need: graphics operations, presentation to our surface, and swap chain support. Swap chain. This is Vulkan's frame buffer system. We make 3 key decisions. Format, we prefer sRGB for correct color. Present mode, mailbox for low latency. FIFO as fallback, and extend, matching the window system size. Image views. The swap chain gives us images, but we access them through views that describe how to interpret the image data. Command pool and buffers. Vulkan commands aren't executed immediately. We record them into command buffers and then submit them to the queue. The pool manages memory for these buffers. Sync objects. Semaphores and fences coordinate the CPU and GPU. GPU is asynchronous. We need to know when it's safe to reuse resources. Okay, and going back to the debug messenger, validation layers are your best friend during development. Whenever there's an issue, and Vulkan is reporting a problem, it will log it for you here. Alright, let's talk about an important concept: frames in flight. The renderer.hpp line 29 shows that we have 2 frames in flight. We prepare 2 frames at once. While the GPU renders frame n, the CPU is preparing frame n plus 1. This keeps both the CPU and GPU busy and improves throughput. Let's talk about the render loop. In begin frame, we wait for the previous frame using the slot to finish, acquire the next swap chain image, reset our fences and command buffer, and then record new commands. The command recording is interesting. Vulkan is explicit about image layouts. Before we can clear the image, we transition it from undefined to transfer destination using a pipeline barrier. Then we clear it. Then we transition to present source so it can be displayed. This explicitness is why Vulkan is so fast. No hidden state changes, no driver guessing what you want. In end-frame, we submit the command buffer to the graphics queue, then present the image. Semaphores ensure the GPU waits for the image to be available before rendering, and waits for rendering to finish before presenting. One note for Mac OS users, Vulkan runs through Molten VK, which translates to metal. We need these portability extensions. This code handles this automatically, but it's worth knowing if you're on a Mac. When you successfully build and run, you will have a window with a gently pulsing dark color. That color animation is just sine waves in main.cpp, nothing fancy. Try resizing the window and the renderer handles swap chain recreation automatically. Now, you might notice some validation errors in the console. This is a semaphore reuse issue. We have 2 frames in flight, but the swap chain has 3 images. When we cycle through our semaphores, one might still be in use by the presentation engine. The validation layer even tells us the fix. Use a separate semaphore per swap chain image, not per frame in flight. We'll address this in the next episode. For now, it runs fine. This is a synchronization edge case that the driver handles gracefully, but we want clean validation output. That's episode 1. We covered a lot of ground. Project structure with CMake, window creation with GLFW, complete Vulkan initialization, frame synchronization, clear color rendering. The code is available at episode 1 tag. Clone it, build it, experiment with it. Next episode, we will add a graphics pipeline and render our first triangle. Thanks for watching.